Welcome back everyone. In this lecture I am going to define the natural numbers using Peano axioms. Indeed, if we assume this axiom of infinity, one can actually prove all the axioms that are appearing in Peano axioms as theorems. Maybe I will leave it to you to think about it. They are not indeed very difficult to prove. So, let us actually begin with Peano axioms. So, the Peano axioms actually defines the set of natural numbers. If we think about it, they are very natural properties of the natural numbers which actually kind of defines them. So, recall what is natural numbers for us. So, they are starting from 0, 1, 2 etc. So, you can actually see that 0 must be an element of n. So, that is the first important property of natural numbers, and whenever n is in n, so then that should imply that the successor of n, which is n plus 1, that should be in n. So, that is my first Peano axiom. So, the first axiom says that 0 is in n and n in n should imply that n plus 1 is in n. Indeed, if we think about it, we do not know what is n plus 1 means. So, indeed, if we actually we call this as successor, sometimes it is okay to actually denote it by like something like n plus plus. Okay. So, recall that each element, even inside the natural numbers, to begin with they are sets. So, because like I said in the beginning, everything is set in mathematics including functions. So, that means elements of natural numbers also should be treated as sets. So, if we have already constructed natural numbers, we expect them to actually satisfy these properties. So, those properties only I am listing and they are called Peano axioms. The second property that we want is that whenever, so maybe let me use this as n plus plus, which is called the successor of n. So, this is what called successor of n. The second property which actually we expect, whenever n plus plus is equal to m plus plus for some n and m belongs to n and m belongs to n. So, then that would imply that n equal to m. That means two successors are equal for some elements of n and m in n. So, then the original elements must be equal. So, this is should be true, and if you think about it, this is same as saying that n plus 1 equal to m plus 1 implies n equal to m. Okay. And the third property that we have, like we should not have any element that is actually successor of 0. So, there is no n in n such that n plus plus is exactly equal to 0. Okay. And the fourth property that we want is what is called principle of mathematical induction, and we will see later that this principle of mathematical induction is equivalent to what is called Villardin principle on n. Anyway, let me just write down this, the principle of mathematical induction and this is again most important property of natural number which come up in many places in mathematics. So, you must have already learned how to use mathematical induction, but let us actually formulate this properly using basics theory. So, you start with a set K, assume that it is subset of n satisfying the following properties, that 0 is in K, and the second property that whenever n is in K implies n plus plus is in K. Okay. So, these two conditions should imply that K is indeed exactly equal to natural numbers. Okay. You have a subset of n satisfying that 0 is in K, and whenever n is there and its successor n plus plus is in K. So, that should imply that K is n. So, this is what we call it as principle of mathematical induction. And like I said, this mathematical induction can be proved to be equivalent to the principle of mathematical strong induction and well ordering principle. Maybe I will come to that later after some time, discussing about how to construct these natural numbers from these ZFC axioms. Okay, so what we want to do is we want to construct an infinite set. Somewhat we want to have a minimal infinite set possible. Okay, if you think in terms of the cardinality. So, let's say that we have understood everything about finite sets. So, we want to have something beyond finite. So, the very first thing to do is construct something infinite, but we do not want like various big infinites. Okay, we want something smaller, like as simple as possible. Okay. So, that is where the natural numbers comes. If you think about it, the axiom of infinity indeed tells you that there is indeed existence of infinity set guaranteed from the axiom of infinity. So, now what we are going to do, we start with the empty set, like it is God given set, using that empty set. So, then we just construct the natural numbers inductively from that set. So, like I said before, so you can actually start with empty. So, empty is like the way to think about it, it is 0. So, basically the set that you are constructing, so the cardinality of that set will be the number that you are going to associate in the natural number. So, then you can think about the singleton empty set. So, which is like empty union the singleton empty set, and this is, if you think about it, the cardinality of this is going to be exactly 1, because there is only singleton empty. So, this is like empty 1. So, now what you do, suppose you have constructed n. So, then from n what do you want to do, from n you want to go to n union the singleton n. So, that is going to be your successor, which is n plus 1, and this is my successor n plus plus. Okay. If I am starting with set empty set, then this procedure actually tells you that you can construct the collection. So, which like you can denote it by like, so this is my 1 and this is my 0 and so on. So, then inductively you have actually constructed these natural numbers. Okay. So, the axiom of infinity guarantees that this set exists, because this is subset of the guaranteed infinite set containing empty set. Okay. So, let us actually go through this once more. So, let us do little example. So, you have started with the empty, from here you have gone to empty union empty. So, this is 0, this is 1. From here if you go, so then you will be having something like this. So, 1 union the empty. So, you have empty union empty union empty. Okay. So, this is going to be your second element. So, if you think about it, so as an element, So, this will have the singleton empty comma this empty union empty. So, this has actually 2 elements, okay, and so on. From here you go. So, now once you know the existence from this axiom of infinity, then all these Peano axioms, so all this can be indeed proved directly from the construction. So, for example, so the meaning of n plus plus being 0 means, so inductively if you have something like this, okay, so n union singleton n is exactly equal to empty, then it is clear that from the construction that n is supposed to be equal to empty. So, there is no other option. Okay. Oh, sorry, what we wanted to prove is that there is no n in n such that n plus plus is 0. So, this would actually tell you that if n union singleton n is empty, so then such n cannot exist, okay, because the way we constructed, we are inductively proceeding to the successors. So, because this set will contain at least singleton n, so that means this n union singleton n is non-empty, okay. So, that is actually comes for free from the construction. And similarly, one can prove that so the first one and second one, they are all true. Okay. I will leave it to you to think about it, it is not very difficult, the formulation is what important. Okay. So, what is more important here is that one should actually understand the mathematical induction properly, and then its equivalent statements of mathematical induction, and then we should also know how to use them in proper places. So, that is what I want to actually talk about now. So, let me just write down all equivalent statements of mathematical inductions. So, now onwards what I am going to do, like I am not going to worry about the construction of natural numbers. So, now we will actually start with the natural numbers itself, and then assuming that how to work with the natural numbers. So, now so we are going to just write down the mathematical induction, the statements. So, let us look at the very first statement, which tells you that if I start with the subset k of n such that 0 is in k, and whenever n is in k implies n plus 1 in k. Okay. So, then we have that k is exactly equal to n. So, this is what mathematical induction says. So, now let us look at the strong induction. So, this is what is called strong induction, and that tells something about like this: you start with A is subset of n such that 0 is in k. So, now instead of having n in k implies n plus 1 in k, what we are going to have is that whenever we know that all this m in n such that m is less than n, this is subset of A, implies that n is in A. Okay. So, then we have again A equal to n. Okay. So, this is what we call it as strong induction. So, in other words, you can see that what we are demanding, that we want this A 2 satisfies the following. So, 0 is in A, and whenever we have that 1 2 etc. k is subset of A, implies k plus 1 is in A. So, then we are guaranteeing that A is equal to n, and this is what we call it as mathematical strong induction. So, now we have what is called this well ordering property or well ordering principle, and well ordering principle for this natural numbers. Okay. So, this actually tells you that so this n with this usual partial order on that n, it is indeed well ordered. Okay. So, that means any non-empty subset of n has a least element inside it. Okay. So, what is the meaning of this? This means if I start with A, which is non-empty subset of n, there exists element A in A such that all elements other than like all elements of A are bigger than this given element A. Okay. This is what this well ordering principle actually says. So, indeed all these three statements are equivalent. Okay. So, let me state it as a theorem that the following statements are indeed equivalent. Okay. We are not actually saying that we can prove mathematical induction. Indeed, one can prove mathematical induction using ZFC axioms, but here what I am discussing now is that more practical thing, that mathematical induction is equivalent to strong mathematical induction and well ordering principle. Okay. To prove that these statements are equivalent, usually what we do, we actually go via this cycle. So, we say that the first statement implies the second statement, and then the second statement implies the third statement, and the third statement indeed implies the first statement. Okay. Then you can see that from this you can actually go from any statement to any other statement, like 2 implies 3, 3 implies 1, then 1 implies 2. So, you can actually go from 2 to 3, again 2 to 1 and so on. Okay. So, this is how we prove actually these three statements are equivalent. So, we are not actually checking the truthness of any of the statement, we are just simply saying that these three statements are equivalent. Whenever you are allowed to use mathematical induction, you are allowed to use mathematical strong induction, and you are allowed to use well ordering principle. Okay. And if you think about it, whenever you are considering the natural numbers, this well ordering principle seems to be very natural, because we use it all the time, that any given non-empty set of natural numbers, they must have a least element, and which is equivalent to the induction principle. Sometime you may be wondering that why induction principle actually works, and you have a reason now, because it is equivalent to well ordering principle. So, in particularly I am allowed to use the induction principle. Okay. So, let us actually prove this. So, let us assume that the statement is 1, assume that the mathematical statement 1 is true. Okay. So, now we claim that the statement 2 is true. So, that means to prove this, we have to begin with a set A of natural numbers such that 0 is in A. So, that is the first condition, and the second condition, if this 1 to k is subset of A, should imply that k plus 1 is in A. Okay. So, this is what given to us. Okay. This is what given to us. Now, we need to check. Okay. We need to check that n is exactly equal to a. So, this is what we need to check. But the thing is, we need to use only the first statement, mathematical induction 1. So, we need to use only the mathematical induction 1. Okay. So, that means to use the mathematical induction 1, we need to construct another set related to A, of course. Then using that, we can easily say that that set being n is same as A being n. Okay. So, how do we approach this? If you think about it, it says that the strong induction seems to be much stronger than the original mathematical induction, because it demands that you need to have all the elements from 1 to k to be in A to guarantee that k plus 1 is in A. Okay. But in mathematical induction, you only demand that k is in A, that should imply k plus 1 is in A. Okay. That immediately implies k plus 1 is in A. So, that means this seems to be stronger, but if you think about it, we are starting with 0. So, that means from 0 one will be able to reach wherever they are supposed to reach. So, that means what I can do, I can construct this B, which is those elements, let us say n in n, such that this n is inside our okay, let's write it like this, 1 to etc. n is indeed subset of A. Okay. So, sorry, 0, 1, 2, etc. Now, if you think about it, this is subset of n. Now, let us check that this B is indeed satisfies the hypothesis of A. So, note that before that B equal to n would imply immediately that A equal to n, because B collects all possible natural numbers such that 0 to n is subset of A. If B is n, then that means A contains all the natural numbers. So, we need to only check B is n. Okay. To check B is n, let us check that B satisfies the hypothesis of this first mathematical induction, which says that 0 should be there, and whenever n is in k, n plus 1 should be in k. So, now let us see, obviously singleton 0 is subset of A, that would imply 0 is in B. Okay. So, 1 is true. Now, if we take this n is in B, that would imply that 1 to n is subset of A. That would imply that n plus 1 is in A using the hypothesis of 2. Okay. This comes from mi2. Okay. So, that means that 1 2 etc. 0 1 2 etc. n plus 1 is indeed subset of A, and that would imply immediately that n plus 1 is an element of B. So, that means we have verified that B satisfies this following condition: 0 is in B, and whenever n is in B implies that n plus 1 is in B. So, this thing immediately implies using mi1 that B equal to n, and that would imply that A equal to n. Okay. So, this proves that mi1 implies mi2. Okay. So, now let us actually try to prove mi2 indeed implies mi3, mi2 implies mi3. Okay. So, this is like, if you think about it, again it is not very difficult, but it is little tricky, because we want to say that the partial order that we have it on n is indeed well ordered. Okay, the partial order is the usual order that comes from the from the real numbers. Okay, so what we need to prove? We need to prove that any subset, non-empty subset of natural numbers has a least element. So let us start with A. Okay, so we want to prove. That A has a least element. Okay. Okay, so how do we approach this? So what if it doesn't have a least element? Okay, so then we should get a contradiction. So then we should force A to be empty. So now let us assume that on the contrary A has no least element. Okay, so assume that A has no least element. Okay, then look at this B, which is the complement of A. Okay, so now if you think about it, if 0 is in A, then that would imply that 0 is the least element. So that would imply that 0 is the least element, because 0 is the least element of natural number itself. So if 0 is there, then you have the least element. But we have assumed that it has no least element, that would imply that 0 is not in A. Okay, this is a contradiction. So that implies that 0 is not in A, that means 0 is in B. So now you have 0 is in B. So now if you go back to your mathematical induction 2, I want to say that B is full natural numbers. So then that would imply A equal to empty. So if we prove that B is exactly n, then we get that A equal to empty, which is again a contradiction. Okay, leads to contradiction. So that is what we are aiming to prove. So that means we need to verify that B satisfies the hypothesis of Mi2. So B satisfies the hypothesis of Mi2. So we already verified 0 is in B. Now we need to verify that whenever 0, 1 to n is subset of A. Okay, sorry, it's B, then that should imply that n plus 1 should be element of B. But if you think about it, if 0, 1 etc. n, if it is subset of B, then that would immediately imply that 0, 1 etc. n, they are not elements of A. Okay. Now, if n plus 1 is an element of A, then that will imply that n plus 1 is least element. Okay. And n plus 1 is an element of A, that would mean that n plus 1 is a least element of A, which is a contradiction, because we assume that this A has no least element. So that means that n plus 1 should not be in A. That implies that n plus 1 is indeed in B. Okay, this is what we wanted to prove. Okay, we proved it. Okay. So the way we construct the sets, that actually tells us that so we can actually get what we wanted. Okay. So this implies that B is n using Mi2. So that implies that A is empty, which is a contradiction because we assumed A has no least element, okay, which is not true. So, that it forces that A has least element. Okay, so, now you can actually use well ordering principle to prove that uh, that implies mathematical induction. Again, you can use similar ideas that I already established here in this proofs. Okay, I will leave it to you to check that check that Mi3 indeed implies Mi1. Okay. So, now from this it is clear that like all these three statements that we have actually stated, they are all equivalent. So, the mathematical induction and mathematical strong induction and this well ordering principle, they are all equivalent. And depending upon the situation that we are encountering, each one will have its own merit, and then we will be able to use them wisely to prove statements. Okay, so maybe I will actually do some examples to demonstrate how to use these statements in different places that will require like more analysis. So, maybe I will do it in the next class. I will stop here actually. So, we will see more examples where we can use these different statements to apply in correct situations in the next class. I will stop here.